Greetings and salutations, everybody. This is Jacob. Okay, so how on earth do we solve this problem? I can't make heads or tails of it, you see. If you've attempted to solve this problem, then you know it's a force to be reckoned with. It's nothing to sneeze at, my friends, regardless if you've managed to solve it or not. Oh yes, this problem would certainly cause a few head scratchings to occur, but those head scratchings will stop occurring by the end of this video, of course. So whether you've attempted to solve this problem but failed, or you've solved this problem and want to confirm your solution, or haven't even attempted the problem but want to see the solution regardless, then keep watching, my friends. But pause the video here if you want to take a crack at this problem and haven't already. Okay, so let's start out by calculating the probability that 5 heads turn up in a row. The probability is 1/2 to the power of 5, which is 1/32. I know some of you might have argued that since the probability of 5 heads in a row is 1/32, then on average we have to toss a coin 32 times in order to get 5 heads in a row, which is a very tempting argument to make. Nonetheless, it's an erroneous line of reasoning, unfortunately. It's true that the average number of coin tosses between occurrences of 5 heads in a row is 32 tosses. But the key word here is average, because let's say, for example, that we've already thrown 5 heads in a row. Then another 5 heads in a row can occur on the very next throw, correct? So in that case, the weight is only 1 coin toss. So the 32 throws on average figure takes into account this scenario. But when we're first starting out tossing the coin, then we have no head start to begin with. So how do we figure out the average number of throws we need when we have no head start? So let's assume, again, we've already thrown 5 heads in a row. And the probability of throwing another head is 1/2, correct? And the probability of throwing a tail is 1/2. So half the time you get a weight of 1 coin toss, and the rest of the times you get a weight of 1 plus x coin tosses, where 1 plus x is the desired quantity we're looking for. It's 1 plus x and not x, because the tails we throw after our first 5 heads doesn't contribute to the subsequent 5 heads. So the average between 1 and 1 plus x equals 32, correct? So now we have 1 plus x over 2 equals 32. Which is 2 plus x equals 64, which is x equals 62. So when we don't have a head start, we'd have to toss a coin 62 times on average in order to get 5 heads in a row. So that's our answer, basically. Oh yes. But wait, we're not done yet. I have a lovely variation of this problem, which is a little more computationally interesting, and it uses the same principle pretty much. So if you want to take a crack at that as well, then keep watching, my friends. It's as follows. So how do we tame this beast, you ask? Can't make heads or tails of it, you say. Well, let's start out by calculating the probability of getting 6 different numbers in a row, for starters, and go from there. So the probability of getting 6 different numbers on a die is 1 times 5/6 times 2/3 times 1/2 times 1/3 times 1/6, which is 10/648. So on average, occurrences of 6 different numbers in a row take place every 64.8 rolls. Of course, this average takes into account that we already have a head start, which we don't in this case. So we have to calculate the scenario in which we don't have a head start. So let's assume for a moment that we've already gotten a head start, that we've got 6 different numbers in a row. Let's calculate the probability that another 6 different numbers in a row occurs after 1 roll of the die. Let's assume, for argument's sake, we rolled 1, 2, 3, 4, 5, 6. So the probability of another 6er on the very next roll, in this case, is 1/6, correct? Since only the number 1 can fulfill this requirement in this case, and the probability of rolling a 1 is 1/6, correct? So the probability is 1/6. How about 2 rolls between occurrences of 6 different numbers in a row? Probability in this case is 1/6 times 1/6, which is 1/36. since we need a 2 on the first throw and a 1 on the second throw. And the probability of throwing a 2 and a 1 each is 1 over 6. So how about 3 throws between occurrences? What's the probability of that? Here's where we need to start exercising caution, my friends. Because in this case, there are 3 scenarios where another sixer is achieved after the third throw. One scenario is this one right here. Another is this one. And another is this one. So the probability is 3 over 216, which is 1 over 72. How about 4 rolls? What's the probability of 4 rolls between occurrences? Here there are more scenarios we have to count. There are 13 different scenarios in total. And here's a list of scenarios. And like I said, we need to exercise caution here when enumerating these scenarios because, for example, you can't roll a 2 and then a 1 for your first 2 numbers, because then we will have rolled 6 different numbers after 2 rolls. So this defers to the 2-roll scenario. So we can accidentally enumerate scenarios that belong to previous roll scenarios if we're not careful, my friends. So far, so good. So the probability in this case is 13 over 6 to the power of 4, which is 13 over 1296. So how about 5 rolls between occurrences? In this case, a strong coffee can certainly help with the enumeration. Since there are 71 scenarios total, it'll take you about like 10 or 20 minutes, depending on how fast you calculate. And like I said before, you can easily include scenarios that belong to previous rolls if you're not careful. So here's a list right here. So the probability is 71 over 6 to the power of 5, which is 71 over 7,776. So after 5 rolls, our head start is pretty much neutralized. And it's like we're starting over from scratch. So the probability of X rolls between occurrences is this right here, which is 1 minus 1 over 6, minus 1 over 36, minus 1 over 72, minus 13 over 1296, minus 71 over 7,776, which is 6,007 over 7,776. Which is roughly 77.2%. So just like we did in the first problem, the average of all these rolls will equal 64.8 rolls, and it's the quantity X that we're looking for, a scenario where our head start is either neutralized or we had no head start to begin with, which is the case with both of these problems. We have no head start to begin with. So now we're going to use the weighted means formula, which is this right here. We're going to use the probabilities of each roll scenario as the weights. And since all the probabilities add up to 1, and the denominator of this fraction becomes 1, in this special case of the weighted means formula is pretty much the expected value of all these throw scenarios. So now we have 1 times 1 over 6 plus 2 times 1 over 36 plus 3 times 1 over 72 plus 4 times 13 over 1296 plus 5 times 71 over 7,776 plus 6,007 over 7,776 times x equals 64.8. And we do the calculations and all the algebraic simplifications. We solve for x and we get x equals 82.35. So the average number of times we need to throw a die in order to get 6 different numbers in a row is 82.35 times. And that's all she wrote, my friends. That's your answer. 82.35. And 62 for the previous problem. What you expected or out of left field? Let me know in the comments. So those were fun probability puzzles, weren't they? Even though the math was simple, especially in the first problem, the problem turned out to be quite difficult and counterintuitive. That's the beauty of probability puzzles, my friends. Even though the math is simple most of the times, it doesn't necessarily mean the problem will be easy. Quite the contrary. This one kicked my teeth in, for example. I was spinning my wheels for days, going nowhere, and finally I had to look up the solution. The second problem was one of my concoctions, a twist on the original problem, where I ramped up the complexity. Enumerating all those scenarios was the hardest part of the problem, of course. So I added some computational plot twists to the first problem, and so the second problem was born, which has everything, computational and conceptual difficulty. Oh yes, all in one. That's what you want when constructing a problem, my friends. You want it to have everything under the sun, and then some. So let me know in the comments if you like these puzzles, if you found them difficult, if you solved them another way, upside down, for example. Shoot a puzzle suggestion and a category suggestion my way. Smash those buttons like there's no tomorrow. That's pretty much it, my friends. And I'll see you guys and gals in the next video. Bye-bye.